For this video, we are looking at scenarios where we have objects not simply moving, but they're moving with a very specific scenario of having a constant acceleration. So it's not something moving at a varying, changing speed. It's something that either has a constant zero acceleration, that's kind of boring, or something that is either speeding up or slowing down at a constant rate. And this actually is a pretty fine scenario to work with because there's a lot of things we experience, a lot of scenarios that follow this, or at least can be very closely approximated as behaving this way, constant acceleration. All right. First thing, we need to remind ourselves about vectors because they're really becoming important from this moment forward. Three of our key physics terms are vectors, and there are equations that utilize them, so it's important to understand that. Vectors, for the most part in this class, what we care about the meaning of is that they depend on direction. Okay? 50 miles per hour isn't really a vector. 50 miles per hour north is a vector, and that's very different, 50 miles per hour north, than, say, 50 miles per hour south. If you were going north on 101 at 50 miles per hour, you would end up in a very different location than if you were going south on 101 at 50 miles per hour. So direction matters, and any of the quantities that we use in physics where the direction is important, like speed or velocity, I should say, we call them vectors. Now, if we have to include direction, we could write down 50 miles per hour north every single time, or south, or east, or west. That's a pain, though. All right? Instead, we're going to use a symbol to represent north, or a symbol to represent to the right. And that's going to be a positive or a negative sign. Okay? That makes it easy. One, because I don't have to write out the word left, right, up, down, 38 degrees north by northwest. Also, it's going to work out well because we can put these positive or negative signs into our equations, and our equations will naturally carry through the direction of the objects, and it will help us get the correct answer. All right? So, first of all, positive values of positive 50 meters per second. All right? That, by convention, means right 50 meters per second. Or, especially when we get to vertical motion, positive is usually the upward direction. Negative is usually considered left, or in the future, we'll use it as down. However, you can assign any direction you want as positive. You could say left is positive if you want. Just make sure then you say right is the opposite, or negative, and make sure you're consistent. Okay? All right, for an object that has a constant acceleration, A with this sub-zero, this means like initial, A naught is how you read that. A little zero, subscript zero, A naught, initial acceleration. That's the same as the acceleration it has at the end. If it's missing that little zero, that usually indicates it's the final. You could use, some of you might be familiar with like little I and little f, initial, final. That's fine too. You won't see that too often though, written by me in this class, but whatever. And then if the initial acceleration and the final acceleration are the same, this value here, the average acceleration, that also has to be the same. So if you have constant acceleration, all these things would be the same number. 6, 2, -5, 0. If you have an object that is moving with a constant acceleration, you have these three equations. Number one, v equals v naught, final velocity equals initial velocity plus the object's acceleration times time. Number two, x equals x naught plus v naught t plus 1/2 at squared. The final position is the same, is equal to the initial position plus the initial velocity multiplied by time, plus 1/2 times the object's acceleration multiplied by the time raised to the second power. Number three, v squared equals v naught squared plus 2a delta x. All right, the final velocity of the object squared equals the initial velocity of the object squared plus 2 times the object's acceleration times the object's displacement. I put those parentheses just so it's clear. It's not 2 times a times delta times x. This is delta x, that's displacement. Okay. Again, these equations work when the object has a constant acceleration. You often can't use them if the acceleration is changing. So don't use these if the acceleration is changing over the course of a problem. Okay. Also, usually, since we can always pick our position from the summer assignment, okay, we learned we can always pick our position. Normally, we just say the starting position is 0. So you often might see this equation written without this first term, because if we can choose where we start, well, keep it easy. Start at 0, then that term goes away. That's really it for the notes for the class. After you write that down, here's a problem I have for you. All right, I'm on my bike. I start at rest and I accelerate uniformly for 4 meters. I travel 4 meters with a constant acceleration. And after those 4 meters, I have a velocity of 5 meters per second. Calculate the time it took for me to attain that 5 meters per second. You should just hit pause right now. Try it on your own, in your notes, on a piece of scratch paper. I don't care. Give it a shot. Then I'll go over my solutions. Okay, hopefully you gave it a shot and now we're trying the problem out on our own. Let's see what information I'm given. It says I start at rest. That means my initial velocity was 0. Okay, I accelerate uniformly for 4 meters. Let's say I start at 0, and this problem is all about me traveling those 4 meters, so my final position is 4 meters. Okay, after I travel those 4 meters, I have a final velocity of 5 meters per second. Let's see, do I know time? No, that's actually what it's asking for. Do I know my acceleration? It says I accelerate uniformly, but it doesn't tell me what that acceleration is. So, that's kind of unknown. So I have my known quantities either directly told to me or inferred. And here are my unknowns. So now it's just a matter of looking at the equations and figuring out which ones I want to use. It's asking for time. So if I look up here back at my original 2 equations, I could maybe use this one to solve for time. Maybe I could use this one because this one has a t, this one has a t. This one doesn't have a time. Can't use this one. But I have a problem. Both of these 2 equations that I need to use to find time also have acceleration in them. And I don't yet know the object's acceleration. So this is going to be a 2-step problem. I'm going to use equation 3 to solve for the acceleration. Then, once I know the acceleration, I could plug in to solve for the time. So here I go. I'm going to start off using that 3rd equation, which is v squared equals v naught squared plus 2 times a times delta x. Well, that's going to be 5 squared. I often don't put in the units while I'm just plugging in. It's okay if you don't. You can if you want. Plus 2. Don't know a. That's 4 meters. Oops, I just went back on my word. I won't include the unit. Okay, well, that's 25 equals 4 times 2, 8a. So the acceleration is 25 divided by 8. That's 3.125. That's meters per second squared. Always start with your original equation, plug in, get me an answer with units. That's the first step. However, I still got to solve for time. I'm going to use that first equation. You should get the same answer with either one, though. Now that I know what the acceleration is, I can plug into here. So that's 5 meters per second equals 0 plus 3.125 multiplied by t. So t is equal to 5 divided by 3.125. That gives me an answer of 1.6 seconds. That's my final answer. That took me 1.6 seconds for me to achieve a velocity of 5 meters per second with a constant acceleration after traveling a displacement of 4 meters. Okay, thank you.